Walk onto any modern factory floor, and you will see hundreds of complex machines, sensors, and robotic arms operating in perfect continuous synchronization. But the hardware driving that synchronization rarely comes from a single manufacturer. You might have a motor drive from one company, a central controller from another, and a network of safety sensors from a third. To function together, they need a shared communication standard. In this network overlay, Modbus serves as that baseline. It's a protocol-agnostic messaging system, allowing different pieces of hardware to understand each other. Developed in 1979 to transmit data between early controllers, its core architecture has remained consistent for over 4 decades. Even in an era defined by cloud computing and gigabit fiber optics, this messaging system remains the most widely supported industrial protocol on the planet. Understanding Modbus remains a baseline requirement for the field. It provides the mechanism for hardware from different eras and manufacturers to exchange data without friction. Looking at this schematic, every Modbus network is built entirely around a strict master-slave or client-server hierarchy. The master is the sole director of the network. It is the only device with the authority to initiate a command, request a data point, or begin a conversation. The slave device simply listens. It monitors the network for messages addressed directly to it, executes the requested action, and sends the resulting data back to the master. A slave device cannot speak out of turn. It will never transmit data unprompted, even if a critical error occurs locally. It must wait to be asked. In a typical industrial layout, the master is usually the primary intelligence of the system, like a programmable logic controller or a central SCADA computer. The slaves are the peripheral devices taking physical action or gathering data at the edge, things like variable frequency drives, temperature controllers, or individual flow sensors. To pass these messages, the master and slaves must be physically wired together over a communication medium. This can be a simple 2-wire serial cable, like RS-485, or a standard local area network. This rigid, speak-only spoken to design is highly intentional. By ensuring only one device ever commands the line at a given time, Modbus eliminates the risk of data collisions corrupting the network. While that master-slave hierarchy applies universally, the protocol itself comes in 3 primary variants, which determines exactly how the message data is packaged for transmission. This chart details the 3 distinct types. In the first column is Modbus RTU, which stands for Remote Terminal Unit. RTU is the standard for local serial connections. It transmits data using compact binary code, highly efficient and well-suited for standard RS-485 copper wiring. In the center is Modbus ASCII. Instead of compressed binary, this variant packages the data using alphanumeric text characters. Because text requires more bandwidth, ASCII is slower than RTU. However, because the code can be read directly on a screen without a translator, it simplifies troubleshooting in the field. Finally, on the right is Modbus TCP/IP, the variant engineered for Ethernet networks. This variant takes the core Modbus message, strips away the serial addressing, and wraps it inside a standard TCP/IP network packet. This allows the protocol to utilize high-speed, multi-node Ethernet infrastructure. It is crucial to note that the internal payload, the specific instruction being sent to the machine, remains the same across all 3 variants. Modbus is not tied to any specific physical wire. It is a flexible message format that can ride on anything from basic copper serial lines to gigabit Ethernet cables. Let's trace an actual sequence through this electrical schematic. Here, we have a PLC acting as the master, connected to a variable frequency drive and a touchscreen HMI on a single RS-485 serial bus. The objective is straightforward. The PLC needs to find out how fast the VFD is spinning an external motor, and then update the HMI screen to display that speed to the operator. Step 1. The PLC broadcasts a targeted request onto the shared line, specifically calling out address number 1. The HMI ignores it, but the VFD accepts the message. Step 2. The VFD receives the query, retrieves its internal data, and sends a response packet back to the PLC confirming the motor is running at 1500 RPM. Step 3. The PLC must now push that information to the screen. It initiates a new request calling the HMI's address and sends a write command containing the 1500 RPM value. The screen updates instantly. In reality, That entire three-step communication process executes in just a few milliseconds, and the PLC immediately loops back to step 1 to check the speed again. This continuous, high-speed loop of queries and responses is known as the polling cycle. This rapid, organized sequence of individual questions and answers provides the underlying logic for what looks like simultaneous, complex automation. Because of that straightforward logic, Modbus is deployed everywhere. As you can see in this application grid, it manages data for PLCs, drives factory HMIs, reads commercial energy meters, sets temperature controllers, feeds SCADA networks, and logs moisture levels in smart agriculture. The protocol has maintained this footprint because it is simple to implement, reliable under industrial stress, and open source, meaning it is free for anyone to use. Since there are no licensing fees, almost every major industrial hardware vendor builds native Modbus support into their devices by default. It does have limitations. Over older serial lines, the speed of data transfer is limited by the physical copper wiring itself, making it slower than modern Ethernet alternatives. Furthermore, traditional Modbus transmits data without built-in encryption or authentication, meaning anyone with physical access to the network line can read or manipulate the data. To bring these legacy systems into modern Industry 4.0 environments securely, we bridge the gap. As shown in this layout, legacy Modbus RTU serial networks are fed directly into an edge gateway device. This gateway aggregates the unencrypted serial data, translates it, and wraps it into encrypted Modbus TCP/IP packets before sending it to cloud servers. This integration positions Modbus as the foundational data gathering layer, feeding the specialized information required by modern AI and smart factory systems. A protocol established in the 1970s continues to supply data to modern AI algorithms. This reliability ensures that simple communication standards outlast the specific hardware generations they were built for. Mastering how Modbus translates, packages, and routes data remains a required skill for anyone building a career in industrial automation. Thank you for watching DEVI Automation Solutions. We provide industrial automation, PLC, HMI, SCADA, VFD, AI, IIoT, smart agriculture, home automation, and solar energy solutions. If you enjoyed this video, please like, share, and subscribe to DEVI Automation Solutions. For business inquiries, email us at deviautomationsolutions@gmail.com. Smart technology, powerful solutions, better tomorrow.